So far, we've been looking at compounds. So we've taken a look at what happens when we take two or more elements and cause them to be bonded together. And this all happened through electrons, either the exchange of electrons in the case of an ionic compound or the sharing of electrons in a covalent compound. But electrons can also cause other substances to be stuck together. And the example I wanted to talk about today is what's called metallic bonding. As you probably guessed by the name, this is how metals are held together. Metals have very different properties from other substances. You see, a metal is classified as something that is electrically conductive, is able to conduct heat, is malleable, and is ductile. Now, I'll get to what all of those things actually mean, but in order to understand them, we need to take a look at the actual atomic structure of a metal. You see, a metal has an array of protons, so basically like the nuclei. And so that's why I only drew the little positive charge, but there would be neutrons in here as well. And what happens with a metal is metals tend to have very large orbitals. Those orbitals surround each of the nuclei. And because they are so large, you end up getting a huge amount of overlap in the electron orbitals of a metal. This overlap creates what we would call metallic bonding. And if you take a look at the structure that is starting to form, I know it may look like a bit of a mess, but ultimately it's creating very few spots where electrons could not exist. This creates a very specialized type of thing that we call delocalized electrons. You may often hear to these referred to as a sea of electrons. So what does that actually mean? Well, let's think of an electron right here. Let's say we have an electron that exists, and this is the atom that actually brought it. Now, this electron is not actually bound to that nucleus. You see, it is free to roam wherever it wants. Because there is so much overlap in the orbitals of a metal, this electron is able to flow wherever it would like to go. This orbital overlap ends up causing metals to do the different things that they do. You see, metals can conduct electricity. Why? Well, if you apply some push to electrons, they'll actually flow in a general direction because of that push. If you get some voltage, which is what push for electrons really is, then those electrons will start to flow, and they flow because they're not stuck to any single nucleus in the structure. Metals also have the ability to conduct heat. Just take a look at any piece of cooking equipment that you have, and if it is a pan or anything that is meant to actually cook food on, it is probably made out of metal. So why are they able to conduct heat so well? Again, it's because of the overlap of orbitals. When a substance takes in heat, it actually starts moving even more. If it's a solid, it can't roam freely, but it can start vibrating and shaking in place. So let's say we were to add heat to this atom. It would start shaking and vibrating, but so would its orbital. And its orbital is connected to the atoms around it, so they would start shaking and vibrating, which would happen then to the next orbitals, and that would spread throughout this substance. Because of all of that overlap between the electrons, it allows them to spread movement as well as actually allowing the electrons to roam freely. Metals tend to be quite soft and bendable. This is seen in two major properties of metals: malleability, which is the ability to flatten out metal into a sheet, and ductility, that is the ability to stretch metal into a wire. If you actually think about some metals, think about the wiring in your house is most likely made out of copper, If you think about something like aluminum, we can squish it into a sheet so thin that we can create it into aluminum foil. So we can actually squish metals into tiny thin layers or stretch them into incredibly flexible materials to help us out. So if there's so much orbital overlap, then why are they able to do this? Well, unlike other substances, this overlap isn't really rigid. If a nucleus gets enough force pushed against it, it can actually slide. And when it does that, it will push the other substances or the other metals out of the way. They'll still connect and overlap their orbitals, but they're not necessarily held super tightly. The other thing that we see with metals is they tend to have quite high melting and boiling points. And the reason why is because they have a huge amount of overlap in their electron orbitals. To overcome that, there needs to be a lot of energy added. So metals tend to melt at quite high temperatures, although usually not quite as high as an ionic substance. That being said, it kind of depends on what material it actually is because of the ways that different atoms will respond to heat. One of the other amazing things about metallic bonding is that we can manipulate it quite easily. You see, just by adding in a little bit of other elements, we can totally change the properties of that metal. If we were to just mix in a few different things, then we can change that substance into a totally different thing. A great example would be bronze. You see, bronze is essentially copper where we then mix in a little bit of other metals. Traditionally, this was made out of mixing in tin so that you would get a combination of both copper and tin atoms combined together. The creation of bronze totally revolutionized the world. You see, it led to what we actually call the Bronze Age because instead of a highly flexible, soft material like copper or tin, you got something that was actually quite hard and able to retain its shape that was very, very useful for making materials out of. So we were able to actually create new substances just by mixing those little things in and creating alloys. So how does this actually work? Well, it all has to do with the bonding. You see, if we think about our array of atoms, and if we normally have our metallic bonding taking place, then we have our overlap in their orbitals. But if I were to say mix in another atom, so let's say I put like a carbon atom in place. Well, this carbon atom is now going to interact with all of the other orbitals around it. You see, what it tends to do is actually cause this to become a little bit more rigid. It loses some of that flexibility. And so you change some of the properties of that substance. Just by adding another element into a metal, you can disrupt the metallic bonding in a way that it actually allows it to change the properties. Another really good example would be stainless steel. See, stainless steel is something that we invented to help protect iron. Iron reacts with oxygen really, really easily and creates rust. Rust then gets into the metal and starts ripping it apart and corroding it. In order to prevent this, we add chromium atoms into the steel. When we mix in chromium atoms, they will actually react with the oxygen instead and create a protective outer layer. This protective outer layer will actually prevent the oxygen from reacting with the iron atoms. It isn't perfect though, which is why we call it stainless steel. It actually stains or rusts less than just pure iron does. So changing the properties of a metal is really quite easy just by changing the substances that are in it. We can disrupt that metallic bonding. And that metallic bonding is the key to why metals work the way that they do. We really only have one other type of compound to take a look at, and it's what we would call a polymer. Now, this is going to be a very different type of molecule than anything we've seen so far, so we'll be taking a look at that in our next video. So, thanks for watching, and I'll see you next time.